The first thing we're going to look at is, there's a quick reminder of the conversion for radians. I always think of it as 360 degrees is 2 pi, because in my head I can associate that with a circle. 360 degrees is a circle, and I know the circumference of a circle is 2 pi times the radius, so I can think of 2 pi like a circle. But I suppose technically it really is pi is 180. Okay, arcs and sectors. We certainly know how to find the area of a circle and the circumference of the circle, but what about just a piece of it? Okay, so circumference, of course, is 2 pi r, and area pi r squared. Shouldn't need reminding of that, of course. But if we're just talking about a piece of the circle, so it'll make an angle at the centre. So AB, of course, is what we call an arc. Mind you, there are actually 2 arcs there, remember? There's the minor arc AB and the major. Now, we always assume it's the minor, unless they tell us otherwise. So if I want to find the length of that arc, I know it's going to be the ratio of whatever that angle is at the middle. And this is why using radians comes in handy, because you'll notice what happens if instead of saying theta divided by 360 degrees, I say theta divided by 2 pi radians, the 2 pi's cancel nicely, and we get a very neat little formula, that the length of the arc is simply the radius times the angle. But the angle must be measured in radians for the formula to work. Okay? So length is equal to the radius times the angle. To find the area of the sector, we can do a similar thing. In this case, just the pi's cancel when we look at that ratio. And so we get a half r squared theta for the area of the sector. So 2 simple little formulas. Let's do a simple little example. And I've purposely put 45 degrees there to remind you that's no good. If I want to find the area of the sector or the length of the arc, I need it in radians. So when I go radius times theta, I do not go 5 times 45 degrees, but 5 times pi and 4, because 45 degrees is pi and 4 radians. So we would have 5 pi and 4 centimetres would be the length of that particular arc. And the area, half r squared theta, it's just a substitution question really. There we go, 25 pi and 8. Another sort of question they like to ask are things like, what's the area of the minor segment rather than the whole sector itself? Now, the segment, of course, is the bit cut off by the chord. And so it's the sector that we've just worked out minus the triangle. So some people like to remember that formula, half r squared, then if you factorise the half r squareds out, because remember the triangle, using the sine rule for the area of a triangle, half AB sine C, in this case would be half radius times radius sine theta. So you get a common factor of a half r squared theta, and you get theta minus sine theta. So some people like to remember that formula. I tend to just think of, oh yeah, okay, area of the sector minus area of the triangle. But when we sub in what we need, look at that answer. Is that a thing of beauty or what? Okay, because of course sine of pi and 4 is 1 on root 2, making it all one fraction. And you probably guessed that answer anyway. 25 pi root 2 minus 100 all over 8 root 2 centimetres squared. It's clear, isn't it? All right. Okay, that's all we'll do for today. Just a handful of questions looking at areas and lengths of arcs.